Hi, I'm Clint Hardy.
And I'm Sean Patel, and this is our video for the final project, the EOG-controlled mouse. Electrooculography, or EOG for short, is a measurement of the eye motion. It's measured from 5 electrodes, a pair above and below the eyes, a pair to the left and the right of the eyes, and a ground electrode, to measure the activity of the 6 muscles shown here which control the eyes. The amplitude of the collected signal is usually between 1 and 300 microvolts, and the frequency bandwidth is 0.1 to 10 Hz.
The problem this project is meant to resolve is so that disabled persons would be able to use the computer. If they're unable to use their hands, they're able to control the mouse, and so this project would allow them to be able to access the internet just to gain information. So our goal is to create a hands-free interface for them to use the computer. By using the horizontal and vertical signals generated by the EOG, they'd be able to control the mouse movement. We'd also have the double blanking to trigger a mouse click.
Here's an overall block diagram of our hardware as well as a picture of the circuit on the breadboard. At first, the 2 electrode pairs are amplified by instrumentation amplifiers. Then they pass through second order Salem key low pass and high pass filters. And lastly, we use a programmable gain amplifier, or a PGA, to adjust the gain of the final circuit. These 2 signals are then read by the ADC on our Arduino Leonardo, which interfaces with the computer. The overall gain of the circuit varies between 2500 and 5100 in order to accommodate almost all eye movements.
The software for this project was all implemented in Arduino, and here's a basic flowchart of how the program runs. First, each pair is read into the Arduino using the analog read function. If these signals go outside of bounds set by our thresholds, then it can detect either left or right mouse control or up or down. In the up or down case, if it detects another peak within a certain set time, it'll register this as a double blink instead of moving the mouse, and will instead click the mouse. Shown here is some examples of the code that was implemented in Arduino. On the left side is how the code actually reads in the values detected from the analog pins. This information passed in is then sent into a 10-point moving average filter, just to ensure that we have a more reliable signal. On the right side is an example of a state machine used to detect movement. Shown here is the Y logic that is also used for because the signal is positive for both blinks and for moving the eyes upward, it then has to also set booleans that will create more logic that will then detect peaks for clicks. Shown here is the code used to implement the mouse click function. This is activated once it detects the EOG signal has gone over a certain threshold. Essentially, a timer is activated in which the signal must return back to a normal value, and then it waits for another peak. If no peak is detected within a certain time range, then it assumes that the user wants to move the mouse up, and so the mouse will begin to move upward. Otherwise, a peak will be detected, and then the mouse will click on the screen.
So here we have a live demo of our EOG mouse. Now Clint will try to open the folder on his desktop using his eyes. In conclusion, we've created a method to control the mouse using EOG without use of the hands. Some problems we faced in this project were motion artifacts, where movement of the user's head, or even talking, or even touching the electric cables would cause the system to malfunction. Additionally, we were not able to implement an automatic gain calibration function because of the nature of the EOG signal. Both of these could be improved in order to make the device easier to use. Lastly, it would be helpful to implement this project onto a PCB so that it would reduce noise inherent in a breadboard.